Okay, hi there. I'm quickly making this video because yesterday, I wrote this yesterday. Yesterday in class, we were learning about like pointers and arrays, and he's like explaining like pointer arithmetic, but the problem is the lecturer is only showing examples. He's not really teaching theory. I don't know, maybe we expected to learn the theory from the book or something. But I think that's making it a lot harder for some students than it needs to be. So I just quickly want to explain some of the theory behind what pointer arithmetic is, why you can do it with an array, because that wasn't really explained, I don't think. At least not what I noticed. Um, so to understand how pointers and pointer arithmetic and all that works, you first just need to understand like how types and memory works. Um, So from CMPG121 you should in theory know roughly how memory works. It's just some bytes um, in a list stored sequentially. So like my laptop has 16 gigabytes of memory, so that would be um, 16 gigabytes. That's 16 billion bytes of memory, right? Something along those lines. And then there's like a lot of technical stuff about how memory works exactly, but you don't have to worry about that. From the point of view of the program, it's just one big list, right? And so in C and C++, well, C++ does technically have runtime type information, but you don't have to worry about it. Um, there isn't in the memory stored what type something is. Instead, it's just like the actual value stored in memory. So, for example, this sequence of bytes, if you interpret it, is it really that sequence? Well, whatever, that sequence of bytes, it makes that floating point number, 32-bit floating point number, but it makes that integer. And so like that's very different. So the way you know how to interpret the um, memory is that the compiler just keeps track of the type and then emits the appropriate assembly instructions. And from the point of view of assembly, it's just manipulating memory. It does not care about the type. That's entirely on the compiler's end. And now pointers lets you work with the memory directly. So in some sense, pointers don't have type either, right? So what the pointer is, it's just like I scroll too far. Did I? No. Okay. So a pointer is it's just like an index into this list of bytes, which is the memory. So you can look at the first byte or you can look at the 4 billionth byte. Okay, so that's all that's a pointer is conceptually speaking. Um, if you like go into the details, there's like paging and global descriptor tables and segments and all that, but that's like really low level detail. You don't need to know about that from the program's point of view. From the program's point of view, you have a big list. If you go outside the parts of the list, you're allowed to look at the operating system guilty program, right? So this, by the way, is for 64-bit systems, which, well, most computers these days would be. The lab computers would definitely be 64-bit. I don't think Windows 11 supports 32-bit anymore. However, one of my examples here, you do have to compile in 32-bit just because I can't be bothered to figure out how arguments are passed on a 64-bit system. Anyways, so it is just an index. I think at this point is when I show you the pointers program, right? So, oh no, this is where I show you the bytes program. Why am I in that directory? Oh, that is where I should be. Um, so if I show you the bytes program, this, I'll like put this in a paste and link or something so that you can play around with this. You should be able to compile this with the C++ compiler too. So don't worry about all this. The point being, we have some variables. I have a print bytes function, which prints the bytes of something, right? And I have a few variables here, right? So I have a character, I have an integer, I have a float, and I have a struct. And then also a C string. So we don't work with these in C++ in class really, but this is a character array, essentially. So if I print all of these, I can show you the bytes, like the actual bytes in memory, right? So if I go, okay, so value 0, the character R, and it's just, that's your hexadecimal value. It's just 1 byte. And then you've got your integer, and it's that hexadecimal value. And I believe this is, I don't know if it's little endian or big endian, but least significant digit first. That's in the opposite direction that you usually write numbers. And then if you've got your floating point value, there's your memory. And then your struct, I'll get that. I might as well do the struct now, right? And then you'll see this is a pointer to some characters. So it's a pointer, and there's the pointer. And like for the struct, it's interesting. Um, so first I have an integer, then I have a float, and then I have a character. And what you'll see is there's the integer. The integer is just 4 bytes, right? Then there's 4 bytes of padding, because on a 64-bit system, each time, well, I think actually the integer is four bytes, so each integer can only occur every 4 bytes. However, this floating point number is actually a double, which means it's 8 bytes. So that can only occur every 8 bytes. So you need to add 4 bytes of padding, right? And then once you're done with the double, then you get the character, which there's your character, which is just 1 byte. But then because it's a 64-bit um, executable, the compiler wants all the structures, the size of those structures to be a multiple of 8 bytes. So then there's another 7 bytes of padding. If you actually swap the order of these to put the double after the character, then you'll see you'll get your integer over here, then you'll have your character over here, then you'll have 3 bytes of padding, and then you'll have your pointer, and that will be that. You won't have any of those bytes. So then you actually get a 16-byte structure rather than a 24-byte structure. Okay, so you can see it's just, they're all just binary, right? There's nothing telling you that this is a character. There's nothing telling you that's an integer. There's nothing telling you that's a float. There's nothing telling you this is a structure, right? It's all just random numbers and variable. There's nothing telling you this is a pointer, in fact. This could just be a 64-bit integer. You don't know. So that's what the compiler keeps track of you for. And what you can also do is you can take some bytes, right? So I have some bytes in memory, and you'll see I basically just copied the bytes from up here, and all that. And what I can do is I can just tell the compiler. So I say it's array of 8-bit integers, right? Unsigned 8-bit integers. And what I can tell them is actually no, it's a pointer to a character. And I say what character is it pointing to. And it will happily give me my character back. Or I say actually no, it's a pointer to an integer. It will happily give my integer back. I'll say actually no, it's a pointer to a float, and it will happily give my float back. You see, and I can even do the same with the structure. If I'm going to start giving the wrong bytes to the wrong type, then I'm going to get nonsense back, which is why the compiler keeps track of the types. But this is the nice thing about C and C++. You can tell the compiler, actually, I know better than you, and it's another type. You can't do this in something like Python. Anyway, so then you've got like this thing. So once you understand what pointer is, it's just a number, right? Like this, it's just a number. So then you get pointer arithmetic. So I can add and subtract from a pointer. Okay. However, what the compiler does is it makes it a bit more it's a bit more convenient for us. Like you can see, an integer is 4 bytes long. So if I have a pointer to an integer and I add 1 to it, what I want is the next integer in memory, right? And where's the next integer in memory? Well, it's 4 bytes later because, well, this one is 4 bytes long, and only after those 4 bytes can have the next integer. So what the compiler does is when you say add 1 to an integer pointer, it actually adds 4 to the number so that you get the next integer. If I add 1 to a pointer to a double, which is 8 bytes, then it adds 8 to the pointer so that I can get the next double in memory. If I add 1 to a character pointer, it adds 1 to the underlying number so that I can get the next character in memory. If I add 1 to a pointer to the structure, it will add 24 to the underlying thing. So that's the nice thing about having a type attached to a pointer. Well, that's the one. I think it helps your pointer arithmetic. And the second thing is when you dereference the pointer, when you say what's the pointer pointing to, then the compiler knows what type to interpret the memory as, right? Um, so those are the two convenience things it adds. Then you also get the void pointer, which is basically saying, I don't know the type of this pointer, or at least the compiler shouldn't keep track of the type, right? So I know what I'm doing. Don't worry about it. You don't need to keep track of the type. That's what the void pointer does. Um, Yes. So the nice thing about void pointer is I don't know about C++, but in C you can convert any pointer to a void pointer silently. So for example, the free function takes a void pointer so that you can pass a pointer to any type and free the memory. And then if you add and subtract from the pointer, it operates directly on the number. So if I add 1 to a void pointer, it adds 1 to the index into the memory array. If I subtract 10, it subtracts 10 because there's no size attached to it. Um, yeah, and sometimes, like, you could also, I think, well, I don't actually know how Python's internals works, except that it's programmed in C, but I wouldn't be surprised if a Python object, the memory which the object owns, is stored in a void pointer. So then you have a value that says which type is it, and you have a pointer to some memory. And then at runtime, you look which type is it, and then according to that type, you interpret the memory because at compile time, you don't know what the type is yet. Whereas in C++ and C, most of the time, you're going to know at compile time. But you can also do that with a void pointer. I don't know what the type is going to be yet. That's going to be determined by runtime. So then I use my void pointer, and then when I know what my type is, I can convert it. Okay, so I think, yes, then pointers.c, I think, demonstrates this pointer arithmetic. Yes, that's what he does. So this is the one you need to compile as a 32, but it's executable. Um, because yeah. So what I'm doing here is I just have my function and I'm passing it my three variables. The reason I'm doing it with this is the variables get passed in a very specific order. So I know exactly where they are in memory, which means I can do all of this. Whereas like if I declare them on a stack, like the compiler might randomize the order for security reasons or something, and I don't want to deal with that. Pointers. So what I'm doing here, right, is my function takes a few numbers, and I know there'll be one, all the numbers will come one after each other in memory. Okay, so I can print my arguments that the function got, 1, 2, 3, just as expected, and I can print where they sit in the memory. So these pointers, remember, they're just indexed into the memory array. So there's my first number, there's my second number, there's my third number. You'll see it goes there, you add 4 to the address, you add 4 to the address again, because each integer is 4 bytes wide. So the next integer has to be 4 bytes later. It could also be 8 bytes later, but in general, if you have an array or something, it's going to be packed closely. I think because it's 30, I'm compiling this as a 32-bit program, um, I'm getting into a bit of like the weeds here that you don't typically have to worry about, but because these are being pushed to the stack is aligned to 4 bytes because that's the word size of a 32-bit program. So like a character would be 1 byte and then 3 bytes of character of padding, and only then would the next argument come. If I had a 64-byte value, it would take up 2 stack slots, right? So on a 64-bit program, you'd have the 4 bytes for the integer and then another 4 padding bytes because each stack slot is 8 bytes wide, and only then you'd get your next argument. But I also don't know in which order they are passed on the stack. Presumably the same, but I can't be bothered to figure that out. Anyways, then we can do some pointer arithmetic. So if I just store the pointer to my first argument, which is lowest address on the stack, I can play around with it. So what if I add 1 to the pointer? Well, your compiler knows it's an integer, it's 4 bytes wide, so I must actually add 4 to the memory index. If I add 2 to my integer pointer, I add 8 to my memory index. Okay? And then if I say, well, actually this is a void pointer, I don't know what type it is, add 1. Now it only adds 1 because it says, okay, I don't know what type it is, so I'm not going to make assumptions about how large the value is. Now if I add 4 and I add 8, then I get the address of the next argument and the argument after that. And what I can also do is dereference my pointer. I'm asking what value is the pointer pointing to in memory. And then, so 1 is my first argument. If I add 1, I get my next argument, which is 2. If I add 2, I get my next argument, which is 3. So yeah, that's nice and simple. Um, so that's the basics of pointer arithmetic. Is there something else I wanted to say? Yeah, I don't think there's much else. What I could also in theory do is say, um, if I say, actually it's a void pointer, and I add 8, and then I'm gonna complain, I don't know how to dereference it, I don't know what type is there, I don't know how to interpret it, so I just have to tell it it's an integer, pinky promise, don't worry about it, and the compiler is going to trust me, which maybe isn't a good idea, but it's going to do that. So then I just do GCC and 32 pointers.c output pointers, and then I select again, and it works. So you can tell the compiler, don't worry about it, I know what I'm doing, and it will trust me. That's the nice thing about C. It's also a very dangerous thing. You can do the same in C++. Like, what I can do is I can tell it, I can tell it X C++. That means I pretty promise this is a C++ program, even though the file extension is telling you it's C. Because if I don't pass this, the compiler is going to look at that .c and it's going to tell me now that's a C program and it's going to compile it as a C program. Aha. You see, now it's giving me warnings. So C++ is a lot more strict about this sort of a thing, so it will yell at you. However, it's only warnings, it's not errors. So if I do that, it still works. Anyway, uh, yes. So now, how does this lead into arrays? So an array is just like a collection of values, one after each other in memory, and arrays are packed. So that means if I have an array of characters, each next character is going to be 1 byte later in memory. If I have an array of integers, each one's going to be 4 bytes later, no matter the word size. Um, well, if your integer is 4 bytes long, if you have an 8 byte integer, then each integer is going to be 8 bytes later. Although do note that booleans are a 1 byte type. There are no 1 bit types. If you want packed booleans so that you have 8 in a byte, then you want to use the bitmap type. Um, anyways, where was I going with that? Yeah, so now it's the arrays program. So you have they're one after each other in memory. However, the compiler doesn't work with that directly, right? Because otherwise, if I'm going to pass an array of 1,000 elements to a function, now I have to allocate memory for 1,000 elements um, for that function, and then I have to copy all of them over for the function to work with. And that's just like really inefficient. So the compiler doesn't do that. What it instead does is it allocates the memory for the array once somewhere, and from then on, it just treats the array as a pointer. The array is nothing more than a pointer, although it's a little bit special because if I put in an array with a fixed size inside a structure, for example, and the compiler knows it's an array of 24 integers, the structure size is going to be big enough to put 24 integers in there, and that's where the array is going to live. But if you interact with that array, it still looks like just a pointer. If you pass it to a function, it's just going to be a pointer to the inside of the structure. Right? It's not actually passing the values around. It's only passing the pointer around. So how the array is allocated is really more of an implementation detail. And then also, this thing, you can't do this in general. Like if I pass an array to a function, I can't do this. I can only do that when the size of the array is known at compile time. So for example, here, because it's allocated on the stack, it's known at compile time. Um, oh yeah, another important thing is you can have any type in an array, right? Types are just like their values in memory. It can be any type you want, but you can only have a single type in an array. You can't have an array of integers and floats. You can have an array of a structure which contains both integers and floats. You can have a union, which I don't know if you're doing unions this semester. You can have a union of integers and floats, but you can't have a mixed structure of a mixed array of integers and floats. It's an array of integers or it's an array of floats, right? So you can read this babbling if you want to. I'm gonna like put this in the description or something. I'm not going to read it out for you. Um, so I am going to read what the array actually looks like. Is it's a pointer to the first value in the array, right? So I think I've said that roughly. So if, for example, if I have this array here, 1, 2, 3, 13, 42, 169, that's 13 squared if you were wondering. Um, and I have the length of my array. Okay, then let me print some stuff. So if I do arrays, so if I print the array, well, it's just a pointer in memory. Okay, and I can index into the array, right? So I get 1, 2, 3, 13, 42, 169, just as you expect. Then I use the address of operator and I say, what's the address of the first element? Well, same as the array. What's the address of the second element? 4 bytes later, so the array plus 1, because remember, it's an integer array. So it's a pointer to integer. So if you add 1, you get 4 bytes later or 1 integer later. And you get the second element is another 4 bytes later, third element another 4 bytes. See in hexadecimal is 12, another integer, another 4 bytes later, because 16 is 10 in the hexadecimal, and the last one is another 4 bytes later. Okay, happy, happy. This leads to pointer arithmetic. So if I can just, well, if the array is just a pointer and the address of each element of the array is just adding that to the pointer, well, I can just add the index to the array to get the pointer to the different values of the array. Quick and simple, easy, easy, right? And then, well, I've got a pointer to the integer. I can just dereference the pointer. So I can just write that instead of array indexing. So that's how you use pointer arithmetic to access an array. It's I don't know if I've explained it properly, right? I'm not very good at like explaining and teaching. However, once you get to understand it, it's quite simple. It's nothing really difficult about this. Yeah, and then, but the interesting thing you'll notice about that is, well, if I have, uh, what am I doing? If I have, uh, I can't remember. Um, Let me do this instead. So, if I have that array plus I is equal to array I, well, plus is commutative. So then I also have that I plus array is equal to array I, but isn't I plus array actually I indexed with the array? And indeed it is. In C, well, in C, your array operator is your indexing operator is actually, and let me just zoom in for you here. It's a bit small what I wrote there, right? So you have that equals that, and so by commutativity of the past, you can also add the index before the array instead of adding it after the array, which means you can index with your array rather than indexing your array with the index. Um, and those are equivalent in C because in C, array indexing is literally just pointer arithmetic. Array indexing is literally just pointer arithmetic in C. In C++, if you have a C style array, then array indexing is also literally just pointer arithmetic. However, C++ allows um, operator overloading. And what operator overloading means is indexing a vector, for example, or a std array, the array from the standard library. That's a class. So then you're using the indexing operator, which is actually a function, in which case you can't do it the other way around. I could quickly write an example about it. Like I'll put all this code like in up somewhere and like link it in the description for you if I can put links. I don't know if YouTube is going to allow me to put links, but I'll try my best. Yeah. So if I do example C++ function and I do include array dot, I think it's just array in main. Uh, I'll be using a cd. I just do c out I and line. You are not happy with me. Okay, that's because I need IO string. Okay, and then I can just do C++ enter cd let you know, out, and then I get please work. Yes, it works. My computer's suffering with the coding. I'm also going to need to plug it in because I'm going to run out of battery. So if I have like an array of integers, it goes 1, 2, 3, and then I can just do like array 1 to get 2 out, and that works. And I can also do 1 array, and that works. Right, so that works, 2, 2, just as you expect. However, if instead of having that, I have array integer 3, and I do that, well, the first one works. Um, right, that one works. However, if I do that one, then you're going to see my compiler is going to give me an error, and it's going to be one of those. Well, it's actually not that nasty. Sometimes C++ errors get quite nasty. You'll see it's complaining about no match for operator square brackets. So that's because what that's actually doing is that's not doing pointer arithmetic. What that's doing is it's calling array. No, array is a local variable. So it's calling array dot operator square bracket 1. That's what it's doing. And what that syntax trigger for actually is I do type of, I think, yeah, type of array, okay, which gives you array in 3, operator that, then I take my, I think it's a pointer to the array, and then I pass 1. Is that? Um, C++ isn't liking that for some reason. Okay, well, okay, C++ doesn't like my usage of type of there, but what I can do is just say array in 3, I believe. I'm not as well versed in C++ as I am, I see. Call to a non-static member function without an object argument. Do you want me to do that? No. I did give you your pointer. I don't know what you are complaining of. Yeah, you're saying std array in 3 pointer to it and then an integer. What I gave you is a pointer to an std array int and then an integer. So I don't know how C++'s syntax trigger works. It's been a long time since I've done cursed stuff like that in C++. Um, However, conceptually, that means that. Uh, and so what that would mean is if I did one dot operator that array. which, well, one doesn't have an operator opening bracket, close bracket, so I can't do that. So yeah, and that also like tells you how you can like make your own. You can do class to public, and I am used to Rust there. Wait, no. Do I need to use the semicolon? Yes, I do. It's Rust, you don't put the semicolon. And I can do, I don't need a construction. I can say um, string, I need to import. I'm going way off topic here. I've already taught you everything you need to know. You can click off the video if you want. This is just interesting to me. String operator there, and I take an array of three integers because why not? And what I return is ball. Right, I can do that if I want, and then I can say out foo indexed with array. You can do curse stuff with that, which is why people don't like operator overloading. I think it's absolutely amazing that you can do curse stuff like that. If you want to make trivia about cursed stuff, you can do in C++. It's not necessarily amazing for actually making serious programs. Sometimes it's, I don't know. As a hobby programming language, I prefer C personally. It's just a lot simpler. You don't have to think about this sort of stuff. But I do think this sort of stuff is amazing. The fact that you can do it, um, because this is just cursed. It's cursed in a different way than the C one is where you can do one array. It's like this is also cursed, but they've cursed in a different sort of a way, and I found both of them very entertaining. But yeah, that's pretty much all I have to say. Enjoy your day. I hope this helps. Uh, yes, this probably isn't the best video ever, but I hope it helps you somewhat getting some of the theory explained to you.